Thank you very much for letting us taking part into this wonderful workshop that is bridging many different topics together, and it's refreshing to see with a new eye things that we considered familiar. That is the Renormalization Group, and I hope I will make myself clear, although coming from a physicist background. So, okay, so the talk will be structured as follows. I will start with an introduction that gives a broad motivation on what we are doing. Then I will give our view on renormalization, and I will present a survey of the basic results of tensor models. Then I will present 3 different roads that may help tensor models to be connected more concretely to higher dimensional non-trivial geometries. That is multiple scalings, flowing to using the renormalization group in a modified way, and defining a quantum field theory on random geometries. I will end with some conclusions and open questions. So let's start. We use the perspective that a quantum theory of gravity is given by a theory of random geometry. We'll also use the functional integration quantization, which in Euclidean signature is reading as follows. So the partition function of the system is given by a sum over different configurations, geometric, and the exponential of minus the Einstein-Hilbert action integrated over the different metrics. Of course, the measure of the metrics and even the ensemble of geometric configurations have to be precisely defined. But this leads to a difficulty, that is that in 4 dimensions, this theory is perturbatively not renormalizable, which means that Einstein's theory is not a UV complete, so you cannot define it at arbitrarily high energies. But in 2 dimensions, such program where you discretize your geometries with random matrix models led to very successful ways to explore quantum gravity non-perturbatively and ab initio. In order to generalize this picture to higher dimensions, the tensor track has been developed, and Vincent has written a number of reviews on this program over the last years that I joined for the last 2. So our picture of renormalization is the following. Physics is mathematics plus scales. And since the 30s, the idea that physics also depends on the... Is it all right?
Yes, it's back. The sound is back.
So since the 30s, the idea that physics also depends on the probing scale was developed independently in particle physics and condensed matter. So the first community resulted into dressing an elementary particle with an effective or renormalized charge. And in condensed matter, they were using block spin transformations in order to recover scaling laws near critical points of phase transitions. But later in the 70s, Wilson managed to fuse both points of view by understanding that you could obtain an effective action by integrating out higher fluctuations of the theory at higher energy scales, and by changing the probing scale, you could change the effective action. And so this is the Wilson's picture of renormalization group flow. So you integrate out your degrees of freedom from high energies to low energies, and you have an effective action. More concretely, if you have a quantum field theory defined by a number of dimensionless couplings, after regularization, they will flow with a probing scale according to beta functions that depend on the other couplings. So a picture of the flow is given here. From this flow, you have interesting features such as the fixed points, which can be ultraviolet or infrared, and they form universality classes of the quantum field theories. that are characterized by symmetries, space-time dimensions, or still number of degrees of freedom. Also, the important directions in this flow are relevant ones that flow outwards a fixed point, irrelevant that go towards it, or marginal that just don't change in the flow. Also, we'll speak of asymptotic freedom, which means that the fixed point is ultraviolet. The ultraviolet fixed point is Gaussian. And further, we say that a theory is renormalizable if it has a finite number of relevant couplings. Now, let's come to tensor models in 0 dimensions. So as I said, they generalize vectors and matrices to higher rank. So they are composed of a field of a rank R, and it transforms under the tensor product representation of a group G that we take of rank N. So here is the transformation with, for instance, the representation of the group for each different index. And their action and observables are defined by this invariance under this representation. And we will call them bubbles. So their action is given by a propagator, Gaussian part, and the interaction part that is basically polynomial in those tensors. So here TD is the coupling of the interaction. And those interactions are represented by R-colored graphs, that I say, those bubbles. So let's make the things a bit more clear by drawing an example. So let's consider a tensor of rank 3 indices, and a unitary group G of size n. So a bubble of size 6, we have 6 tensors. We contract the indices together with deltas. So we represent pictorially the white, the tensor T with a white dot, and it's conjugated by a black one. When two indices are contracted, we draw an edge, and we associate a color to this edge according to the position of the index that is contracted. We do the same for all indices of each tensor, and we obtain, you see, a three-colored graph. But there are different ways that we can also glue the indices pairwise, and this gives different bubbles. Now, how the theory works. So you take this action with a specific interaction set, and you write the partition function. Now, you tailor expand the interaction, the R-colored graphs, and you integrate with respect to the Gaussian measure your fields, which adds an additional zeroth color that we say. So in the end, you obtain R+1 colored graphs for a tensor of rank R. You have to sum over all the different possible weak contractions. And notice the power of n that has been chosen here. So if you keep this scaling of n with no other rescaling with respect to n of your couplings, Gouraud has showed that the amplitudes that that are relevant for the vacuum graphs are scaling like this. So you see that you have an extra integer here, or half integer, that's called the Gouraud degree, that discriminates between the different graphs. And this degree is given by the sum over the different jackets, the genera of the jackets. And jackets are embeddings of the color graph on the plane, so they have a genus. And further, Gouraud showed that the graphs that dominate the vacuum graphs form a class that is called melonic. And this class has a very peculiar structure. That is, it's formed by self-insertion of the fundamental melon. So I will show here how this works. So you insert on each edge. You can take this one, for instance, and you insert the fundamental melon. You can do it again and again, and so on. And this peculiar process allows the melons to be counted by rooted R+1 array trees. So here I represent on the right the associate picture for what is the tree that corresponds to the melon. So here it's growing. But you can decide to scale your couplings differently with another power event, such that you may hope to reach a richer structure instead of melons. So, for instance, this has been managed for a peculiar type of interactions that is called maximally single trace. So they are peculiar in the sense that they have one phase for each pair of colors, and a phase is a cycle of two colors. So you have, for instance, green, red, or green, blue, that is one phase. And they showed that with this peculiar scaling that depends on the number of phases of the bubble, they could obtain generalized melonic graphs, where here the black line corresponds to the 0th color that I told before, and the dot corresponds to this peculiar vertex that has been shrinked to a point. But as you can imagine, this still corresponds to trees. Now I want to show the different Large-N limits that have been obtained in general field theory. So you have vectors, matrices, and tensors. For vectors, the different graphs are discriminated by the number of loops of bubbles. So here it's a tree of bubbles. For matrices, it is discriminated by the genus of the embedding surface. And for tensors, it is the Gouraud degree. The first and the third class have a continuum limit that is characterized by branched polymers that have a Hausdorff dimension 2 and a spectral dimension 4/3. For matrices, the continuum limit is the Brownian sphere with Hausdorff dimension 4 and spectral dimension 2. The different connected invariants that you can build for the different field theories are also very different. For vectors, you have a single one. For matrices, one per number of matrices involved. But for tensors, it grows factorially in the number of vertices.
Can we interrupt you with a naive question?
Of course.
Could you give an intuitive idea why the matrix models lead to a Brownian sphere, unlike the other two, which leads to polymer? Can we get an intuition for that?
So it's difficult to say intuitively, but it really comes from the fact that the first and the last class have a Large-N limit that is given by trees, so tree-like graphs. And when even when you make that's not enough to grow a continuous surface two-dimensional, if that's intuitive enough.
And why does the matrix model not?
Yes, because it's in the Large-N limit they have all planar graphs. It's just genus 0 that constitutes the Large-N limit, and so after that you have to understand how they have a different spectral, a different Hausdorff dimension that is given by the it's a bit more difficult to explain intuitively, but at least you can understand the spectral dimension 2.
Okay.
It is given by the fact that the leading order is planar.
Thank you.
And so the holographically, in holographic theory, the vector models have been connected to higher spin theories, matrix theories to string theory, but for tensors, the holographic dual is still largely unknown. Nevertheless, in the last few years, there has been a surprise coming from string theory in the name of the Sardev-Kitaev model, which is a quantum system of n-Majorana fermions living at the temperature 1/beta, and they have an extra coupling here, J, that is taken quenched. So that is when you compute correlation functions, you have, in order to, before, let's say, you compute your theory, your correlation function at fixed j, and then you have to average as well over j, which is taken here Gaussian. In the large n and strong coupling limit, they have the peculiar features they have shown that you have an approximator parameterization symmetry and also saturation of a specific chaos bound defined by Maldacena and collaborators. And those features make it the simplest model of holography in the sense of it is 2 CFT1. And it has led to, yes?
Sorry, could you stop 1 minute to explain to us mathematicians what these words are, holography and the correspondence ADS CFT, just a super...
Okay, in one word, it makes, one sentence, it makes a, so you have two theories that live in different dimensions that have been shown conjectured dual. That is, so you have a gravitational theory living in d+1 dimensions with a specific boundary. And on this boundary, you have a quantum theory, so no gravitation, that is supposed to be dual. So when you make a computation in the d+1 dimensional one, so the bulk, it says, it should have a dual in the a dual computation in the boundary theory. And so here you have the ADS2, so which means a geometry with negative curvature in 2 dimensions that is dual to a conformal field theory in 1 dimension. That's the reason of the one here. Is it succinct enough, or you want a bit more detail?
Thank you. It gives us an idea.
Okay. And so this conjecture was brought in string theory, and many questions resolving around that was regarding solving the black hole information paradox. And this model, although very low dimensional, has brought some insight on that. But what I want to emphasize is that the two features here appear because the limit is melonic. And so Witten very quickly showed that the one-dimensional tensor models also present the same features, and this motivated the study for larger dimensional tensor models. So here a very packed slide to show the different topics that have evolved since the discovery of the large n limit. That go from combinatorics, counting invariance, to turbulence or data analysis recently. And in red, that is the blessing, but also the curse of tensor models. That is, their large n limit is given by branched polymers. And what we want is to get beyond that. So to make they are supposed to pave, to discretize higher dimensional geometries through their Feynman diagrams. And that's difficult to escape, to come up with, actually. So the first road is concerned with multiple scalings. So as I said, to go beyond the results of Gros and Ryan, that the melons are branch polymers in the leading order limit, we need to incorporate subleading corrections in 1/n. And the first try that has been actually worked out first for matrices is to consider the double scaling limit. So you write, for instance, the simplest model, you take the partition function of a quartic matrix model with coupling lambda, and notice here the peculiar scaling in n that has been put up front. Then in the free energy, that is the logarithm of the partition function, the different Feynman diagrams of different genus are coming with a different power of n. As I was saying, so leading order, they are planar. And Fg is the generating series of genus G rebound graphs. So they are holomorphic in a certain domain of lambda, and they meet a singularity at a critical point, lambda c. The behavior around this critical point is of this form. So they have you have a constant G, and a power behavior, where chi is the Euler characteristic, and gamma is, for the model we consider, is -1/2, but it could be m for more generic interactions, higher order. Then, so at the when you approach the diverging point, you take the double scaling limit by sending n to infinity and lambda to the critical point in a correlated way, such that you keep x that has this peculiar relation in n and lambda minus lambda c. You keep this x constant. This allows you to write the free energy as a power series in x, and k behaves as 2g factorial since it results from the sum over all Feynman diagrams. And the interesting feature was that it was related to integrable minimal models, and it has been worked out by many people since the 90s.
May I ask the question? The asymptotic behavior of FG around the critical value, is that an assumption? Is that
No. That's you can work out for specific genus. You evaluate the series, and it can be shown as that. So that's among those people. I don't know exactly which one, but they have shown that.
Thank you.
So, as well as for matrix models, the tensors also have, some people have also worked out a double scaling limit for tensors, Dartois, Gouraud, and Vincent actually. And in a quartic interacting model of rank R with a coupling lambda, you can introduce this variable x, and by sending n to infinity and lambda to -1/4 the rank, you keep x constant, and then you find that the 2-point function has this peculiar expansion in x. It itself has a new critical point, so beyond which it does not converge anymore, at xc, which is 1/4 r minus 1. And its behavior near this new critical point is of a power law type, which again corresponds to the branch polymer phase. But beyond over sextic rank, so you can the series is not summable. So you again have a divergence. So to summarize, contrary to matrix models, the double scaling limit of tensors still resums only triangulations of the sphere, which is much less than general triangulations that you would hope for. And in further contrast to matrix models, at least for the rank 6, there is also a triple scaling limit, hinted, but it has not yet been worked out. And interestingly, the quartic tensor model can be mapped to a Hubbard-Stratonovich through a Hubbard-Stratonovich transformation to multi-matrix models, which, without the leading order, satisfy blob topological recursion. And to this, I point to Reimar Vulkenar's talk. So, all in all, this road, although is what we should aim for, is very difficult to follow straightforwardly because it requires a fine analysis of subleading orders, and this gets quickly involved. So let's go to the second road. When we have no space available, so zero-dimensional tensors, for instance, a way to build a hierarchy, a scalar hierarchy between degrees of freedom is to break the isotropy of the covariance. So the ultraviolet would correspond to lowest covariance, or many degrees of freedom, and the infrared will correspond to highest covariance. And then we have a flow again from the ultraviolet to the infrared, many degrees of freedom to few degrees of freedom. A close but not completely identical picture was hinted 30 years ago by Brezin and Zinjustin. So more concretely, how it works out for our models, you take your propagator and you build a Laplacian in the index space, which makes the such that low indices, so close to so the lower indices will correspond to your infrared, and the when you have your full tensor, this corresponds to your ultraviolet. So when you integrate out the largest components, you build your RG flow. And with a quartic interaction, Joseph Benjeloun showed that the model is renormalizable in rank 5, and it shares with the non-abelian gauge theories the property of being asymptotically free. Since the large N limit consists of only melodic graphs, Vincent has shown that actually this asymptotic freedom is really a combinatorial property, and so it was protected by topological reasons and more general than actually only rank 5.
Sorry, Nicolas, can you say a bit
Yes.
more what does that mean, that it's asymptotically free? I mean,
Yes.
at least in this case of tensor.
So it means that when you so when you have your RG flow, then it means that your theory is Gaussian in your
Gaussian.
full tensor space, but
Asymptotically Gaussian.
yes, you would have something more to say, Vincent?
Oui, oui, mais je passe mon tour.
Yeah. So I think that the idea that I'm explaining just here is that given this more general, even though it's zero-dimensional, you can still have a non-trivial RG flow, and by understanding how what the different fixed point that you obtain, or you may find it's Gaussian, but it's a new repackaging of your tensor degrees of freedom, such that it may seem Gaussian, but it's not Gaussian in your original tensor formulation. So, because in your original tensor formulation you have this melonic limit, but maybe a different fixed point that is also UV would correspond to non-melonic a non-melonic geometry. And actually, so they have with functional renormalization group, Benedetti and Aishon have worked out different models, and in a recent paper they have found a candidate fixed point with two relevant directions, so it has still to be shown if this limit is melonic or not.
I want to say something.
Yes. It's your talk after all.
Fundamental objection of consistency of quantum field theory was raised by Landau, et Politzer et Gross and Wilczek discovered that non-abelian theories are also asymptotically free. This was a discovery, major discovery in physics.
Yeah. Okay. But we can perhaps discuss that the link with gauge theory and gravity, perhaps in the discussion tomorrow.
Je veux commenter dans la table ronde aussi.
Okay. Okay, so I continue.
Oui.
And now the third road which is, in a sense, is going backwards. So instead of having multiple scalings and trying to reach a more complicated geometry than trees, we start by defining a theory, some matter fields that live on branch polymers. So actually really showing that you can obtain such a limit right from the start through a tensor model is still work in progress. But so we have at least started investigating this limit of quantum field theories on trees. So the simplest setting is to take a scalar field on those random trees, which are equivalent to branch polymers. It's the simplest quantum field theory of an ensemble of interesting random geometries. And what we showed was that on average, the standard power counting analysis for the superficial degree of divergence of amplitudes is consistent when using, instead of the dimension, the spectral dimension, which for trees was shown to be 4/3. So this actually leads the way to quantum field theories on more general random geometries. So the tools that we used were the Renormalization Group flow and random walks. So the idea is to decompose the 2-point function as a sum over random walks, an idea that arises from an old work of Szymanczyk in '69. And using precise key kernels of Barlow and Kumagai, we could evaluate generic amplitudes and start a renormalization group analysis. I have to say that this is related to some expansions, random walks or random currents or laces by different people that have been used to analyze rigorously correlation functions for various statistical models and to show triviality of the universality class of phi4 in dimensions larger than 4, larger or equal now, to prove relations between and bounds on critical exponents below the critical dimensions and bounds on beta functions. Nevertheless, it seems hard to go far from to study far from free models using those techniques. So to give you an idea of the random space we were using, you can picture yourself. So it's a rooted binary trees, and we glued two roots together. So in the end, and also at criticality, such that you have an infinite line of integers that we call the spine. On this spine, on each integer, we grow a finite tree with a measure 1/2 to the size of the tree, the number of nodes. And the probability measure on the whole space is taken by the product of the measures on each integer. And you can take expectation values as usual. And also then the spectral dimension is defined as follows. So if you take a random walk that starts from a point X, and you consider the probability that the random walker returns at X in the time t, the spectral dimension is what leads, or what controls the long time decay of this probability. And Witter and collaborators have shown that this spectral dimension was 4/3 for this ensemble. Now, how do we propagate the matter fields? So on a fixed graph, you can define a Laplacian by the difference between the degree matrix and the adjacency matrix. So the degree matrix is telling you how many neighbors you have at each vertex. And the incidence or adjacency matrix tells you how your neighbors are connected. Then the propagator between X and Y is given by the sum over all random walks from X to Y with a peculiar weight for each vertex that you encounter, given by 1/, the degree of the vertex plus some infrared regulator. You can also have a continuous time version of that, where you integrate the heat kernel over all times of the random walk with, again, our infrared propagator, our infrared regulator. We were interested in raising the propagator to a specific power. For that, we used an identity that can be seen as analogous to a Chalen-Lehmann representation, where you integrate your propagator with a peculiar weight for your mass that can be seen as some energy density, for instance. Now, what scaling zeta had we to use? For that, we were using a convention on external legs by Vincent and all paper, such that the infrared degree of divergence of a scalar field of mass dimension d minus 2 zeta over 2 and phi cube interaction is given by the following formula. So you can see that it's actually minus the ultraviolet degree of divergence. And by tuning zeta to this peculiar value, we obtained a just normalizable theory. So d times 1 minus n over q. And the game was to show that this formula agrees when you change d to the spectral dimension. And so by this superficial degree of divergence, you see that for q equal 4, a quartic theory, 2 and 4 point functions needed renormalization. Also, how to do field theory on a disordered space? Usually we have a partition function or a quenched partition function where the space is fixed. Also, you can have correlation functions. When you expand the perturbatively, you obtain Feynman graphs on this fixed graph. But now, when you want to average, you have to take your external points on a space that belongs to all of them. And for this, it was the spine. So by averaging, we obtain annealed expectation values of annealed correlation functions. And so how do we do the renormalization group flow in our setting? So we first do the regularization step, which is to decompose our propagators into proper time slices. So a random walker is only allowed to have its time of propagation ranging in this interval ij. Here m is simply a constant larger than 1. J0 is the ultraviolet cutoff, or you can take it 0. Rho is the infrared cutoff, and all external propagators are put at scale rho. So you can say 0 mass, for instance. And now an amplitude will decompose as a sum over all scale assignments. So all the propagators that are involved in this amplitude have a peculiar are put at a peculiar slice here, ranging from 0 to rho. You have to sum over all those assignments. Then you have to identify the superficial degree of divergence and the diverging graphs that we did earlier, but we had to show that it was correct. And what is important is that at a given assignment, an amplitude is bounded by the product over all the high subgraphs, which are graphs such that the internal legs have a scale that is lower than that of the external legs. Then we do the localization or the renormalization, where we expand the diverging subgraphs around their reference points, and subtracting those diverging terms requires counter terms. And then finally, how renormalization works. So we have to integrate out the lower scales below a certain scale I, and this gives the theory at scale I. Now, a word on the probabilistic estimates of Barlow and Kumagai. So they introduced the concept of lambda good balls. That is a ball for which the volume ranges between the squares, or here the Hausdorff dimension was 2, and notice the peculiar dependence on lambda. And crucially, they showed that those balls were typical. So the probability that a given ball is not lambda good was bounded exponentially by the larger lambda, the larger the probability that the ball is not lambda good. sorry, the larger lambda, the larger you can find a ball that is lambda good. And then given a lambda good ball, then you could, they showed those quenched bounds on the heat kernel. So if the distance is not, the distance between the 2 points is not exceeding a certain quantity, depending on the time of the walk. And this is actually giving the spectral dimension. Now our results, so we first sliced our rescaled propagators, and we showed that the propagators averaged were bounded above and below by this peculiar dependence on M and J. And when you were summing over an endpoint, then the expectation value was again had an upper and lower bound given by this. But what this is telling you is that a typical volume integration, so when you sum over the endpoint, this gives a dimension 2, while in proper time t, the propagator scales as t to the minus 1/3. So it's given by this here. The power of 2 is depends between how you go from t to m. And then for converging graphs, so graphs that had no 2 or 4 point subgraphs, we showed that for graphs that had n internal vertices, we could define the limit of rho sent to infinity, and then the expectation value of those graphs had a uniform bound given by a constant to the power of n and an n factorial with a power of beta that was very preliminary. So how this proof works, we used some Cauchy-Schwarz inequalities and the preceding bounds on the propagators, and we sliced the space into rings of some balls around those external points that we ask them to be lambda good. But when you consider those balls, they have a certain probability to intersect, and you consider those balls to be independent. So we certainly lost factors that led to this factorial growth here with this very crude evaluation.
Can I wait for a comment?
Yes.
These bounds were divided at the Schrödinger Institute.
Yes, exactly. Yeah, 2 years ago. 1 year ago.
Nicolas, can you
Yes.
write it up in 2-3 minutes, please?
Yes, yes. And so we did an analysis also to subtract subtract divergences occurring from 4-point functions, which needed to see how propagators, how you could basically change propagators from one point to another. This was enough to show that actually you could easily renormalize amplitudes that also included 4-point functions. So this is what is depicted in this picture. So what the subtraction procedure is. And now my conclusions. So to summarize, we have 3 roads, as we see, to get beyond melons, either from multiple scalings, using an RG flow and breaking the isotropy of the covariance, or starting with branch polymers and decorate them with a quantum field theory. A preliminary result is that the spectral dimension enters the Renormalization Group power accounting when you work on a random surface or random geometry. And some questions: can we see the large n limit of tensors as a field theory on random trees? When working out the beta functions and so on, is the fixed point corresponding to a CFT? If yes, what is the group? So we are on a fractional dimension space. Does that make sense? is there a saturation of the chaos bound as there was for this SYK model when you work on a quantum field theory on random trees that may reveal the presence of a geometric bulk dual, which would be interesting for tensors, but this requires more precise evaluations of the quartic functions, which is tricky. And can we extend that to other geometries as well, such as, for instance, planar maps or things like that? And that ends my talk. Thank you very much.
Thanks, Nicolas. Is there questions from the audience? We have a few minutes. Let me check. No one raised in. Tell me, Nicolas, if you say that if you have a chaos bound of a CFT of a random tree, your third point, so that you would have a bulk dual, that means you would have a gravity on some bulk that would exist, and this CFT would just be this QFT would just be the CFT part of the ADS CFT duality, or is it completely wrong what I said?
So recently they have extended the holographic picture very recently because of this SYK model that has some disorder also. But we are using a disorder on the underlying geometry, not the coupling. So the idea that we have with Vincent is that the random geometry that we have is sort of making a boundary that is fluctuating. And so the bulk dual would have some intrinsic random geometry parts. For instance, its boundary would be fractal or something like this. So this is what we think would correspond to this bulk dual, but we still need to find the dual.
And so your hypothesis would be that we would live in this bulk dual, and that, or I mean, if everything goes perfectly well, would that be the goal of the program?
Yes. So the goal of the program is really to generalize or to combine the this holography with a random geometry, because quantum gravity intrinsically should correspond to an understanding of random geometries. Mm-hmm. So where are those random geometries in this holography picture? That's yes, that's the question.
Comment on this. It is a picture of vicinity of black holes.
Right. Yes. So the SYK model, the CFT1 that I have shown, and the ADS2 that was shown dual. The ADS2 part is actually more general. It's not just two-dimensional spaces. Right. It's really a zoom on some peculiar black holes that live in higher dimensional spaces. So even if you take a higher dimensional geometry with a black hole inside, you zoom inside, you zoom close to the horizon, and you should find in this subspace, you should find some quantum mechanical, so a dual description with an SYK model. So it's more universal than just one dimension.
Les directions tangentielles sont pas importantes.
Exactly.
The tangential, I'm translating, tangential directions are not important.
All right.
What matters is time, actually. Yes. That's the CFT1.
What matters is time. That's a very beautiful sentence.